So in the last video, we used the Crank-Nicholson method to develop temperature profiles for our thermal diffusion through a bar of a consistent material with a constant thermal diffusivity. And if you remember from our first video, we did a similar thing using just mass and energy balances, but we ran into an issue where through proving it with a von Neumann analysis, we saw that R was only limited to a scheme where R could only be less than or equal to 0.5. However, we find that in our Crank-Nicholson method, all values of R actually do let us converge and do let us develop temperature profiles for our system. However, as our R increases, we actually lose accuracy due to the time jump between two temperature profiles. And we can actually use a von Neumann analysis to develop that theory and prove that theory as well. So where we started off in our last video is we developed this Crank-Nicholson relationship that led us to create a matrix scheme with a sparse matrix rather to allow us to use SciPy's banded matrix solver to develop temperature profiles. And we got that from this equation that I'm writing out here. And plus 1 minus R Tj minus 1. And we also get on the other side, this is equal to R Tj plus 1 times n plus 1 minus 2R Tj times n plus R Tj minus 1 at n. So we can start here for our von Neumann analysis for our Crank-Nicholson method. So actually, there should be a plus 2R. We actually shifted this over from the other side. So this is 1 plus 2R. This is 1 minus 2R. So now what I'm going to do is our ultimate goal with this analysis is we want to relate Tj at time n plus 1. And we want to relate that to this Tj at time n. If we pull out Tj from here, we have a minus R. And this is one position to the right, which is to say that we are shifting by some multiplicative factor of ik delta x. And this solution comes from when we did our first von Neumann analysis in the first video. Similarly, we go on here, and now we have plus this 1 plus 2r factor. That's what's left behind here. And similarly, for the position to the left, we are shifting over by minus ik delta x. So we're just putting this now into the exponential form. Now over here, it's really the same story. Pull out that r, we're moving 1 to the right, so eik delta x plus 1 minus 2r. Write that better. And that is exactly that. And then plus re minus kx minus ikx. Because we're going one position to the left, so we get a minus sign over here. Now, what we know from Euler's theory is that e to the ix is equal to cosine x plus I sine x. Similarly, e to the minus ix is equal to cosine x minus I sine x. So, if we have e to the ix plus e to the minus ix, these actually cancel out here and here, and we get 2 cosine x. So keeping this in mind, we see that we have a e to the ik delta x, and we have an e to the minus ik delta x. We look at these coefficients, we have a minus r and a minus r. So what we get for this side is tj n plus 1, and we can say, how should we put that? Well, why don't I take minus sign out here and get 1 plus 2r, right? Or, yeah, 1 plus 2r. You know, I don't like doing it that way. Let's just say 1 plus 2r minus 2r cosine of k delta x, right? Equal to 2 sub jn. It's the same story here. And now this is 1 minus 2r plus 2r. Go over here. Cosine k delta x. So let's do one last step, and that will kind of show us why this Crank-Nicholson method is better for inputting multiple values of r. So what I'm going to do is I'm going to divide both sides by whatever's in parentheses here, tjn. So on the top, we'll go 1 minus, and we'll factor out a 2r from here, which means that we have a 1 minus cosine k delta x. Let me align. And on the bottom, we get a 1 plus 2r, 1 minus cosine k delta x. Here we go. Now, this here kind of proves why our r value isn't bounded by any number, like how previously we had r bounded to 0.5. And the reason for that is, well, let's take a look at this cosine here. We know that the range for cosine, so cosine of any theta, ranges between 1 and -1. So if cosine, let's say we have -1 here. So 1 minus -1 is 2, and then that's multiplied by some number, and then 1 minus some number bigger than itself will give it a negative number. And on the bottom here, let's say that same thing, cosine -1, 1 minus -1, so that's plus 4 times r, or let's see, 2 times this, 1 minus 4r, and then this is going to be 1 plus 4r down here. So essentially what we're saying is that we have 1 minus some number bigger than itself over 1 plus that same number, which is to say that anything in this parenthesis here can't exceed 1. There is no way for it to possibly exceed 1. So then what we're saying is that this temperature at the next time jump, the magnitude by which that changes must be smaller than the magnitude that n changed from n minus 1. So this kind of proves that this growing function here is bounded and doesn't grow into infinity, which was actually the issue with our previous method, just using our energy balances. The issue was that if r got greater than 0.5, then our temperature growth would grow uncontrollably. There was no way to bound that. Here, we have that we have that intuitive bounding because we have the cosine on top here and the cosine on the bottom here, and we have this number divided by a number greater than itself, which means that either in the positive magnitude or the negative magnitude, it cannot grow any greater than 1. So that kind of just proves why any value of r will work for this Crank-Nicholson method.